Welcome to Calculation Support Webinar 4. This tutorial contains questions from your study days and Boots Learn papers concerning dilutions, moles, half-life and formulas. Calculations Paper A, Question 20. A patient has hypertension and is recommended to be on a sodium-restricted diet. He currently takes Brufen, effervescent granules 600 mg to treat pain. He takes one sachet 3 times a day, and each sachet contains 8.6 millimoles of sodium ions. The maximum daily intake of sodium per day recommended is to be 100 millimoles. 1,000 milligrams of sodium is equivalent to 42.5 millimoles of sodium, and 1,000 milligrams of salt is equivalent to 390 milligrams of sodium. How much salt can he ingest from his diet? Give your answer in grams to 2 decimal places. So the first thing that we're going to highlight for this particular question is the dose. So he takes 3 sachets a day, so that's 1 sachet 3 times a day, and each sachet contains 8.6 millimoles of sodium ions. We are also going to highlight the maximum daily intake of sodium, which is 100 millimoles, as well as the equivalence equations that we have of sodium and salt. The question has asked us how much salt he can ingest from his diet, and the answer needs to be given in grams to 2 decimal places. So the first thing that we need to work out is the total amount of sodium in millimoles ingested from his Brufen. So he takes 3 sachets a day, and each sachet contains 8.6 millimoles of sodium ions. So 8.6 multiplied by 3 equals 25.8 millimoles per day. And the maximum intake of sodium per day is 100 millimoles. And therefore, 100 minus 25.8 is equal to 74.2 millimoles, and that is how much remaining it can be ingested from his diet. But we need to know what this is in grams. So we know that 1,000 milligrams of sodium is equal to 42.5 millimoles of sodium. So how many milligrams are present in 74.2 millimoles? We can work this out by dividing 1,000 by 42.5 and then multiplying out by 74.2 to give us an answer of 1,745.88 milligrams. Now we also know that 390 milligrams of sodium is equal to 1,000 milligrams of salt, which if we convert to grams is 1 gram of salt. So in order to calculate how many grams of salt are contained within 1,745.88 milligrams, we are going to divide 1,000 by 390 and multiply out by 1,745.88 to give us an answer of 4,476.6 milligrams. And if we convert this to grams, we can do this quite simply by dividing by 1,000, which gives us an answer of 4.48 grams. Study Day Calculations Paper 1, Question 3. You are required to make 150 ml of sodium chloride 0.9% solution to fulfill a prescription received in the hospital pharmacy. How many millimoles of chloride are contained in 150 milliliters of sodium chloride solution? The relative molecular mass of sodium is 23 and the relative molecular mass of chloride is 35.5. So the relevant parts of this particular question are 150 milliliters, 0.9% solution, how many millimoles of chloride are contained in 150 milliliters, and the relative molecular masses are important. So 0.9% means 0.9 grams are present in 100 milliliters. So I'm just going to pop this down now. We don't actually know how many grams are present in 150 mils, and that is what we are required to make. So I'm going to put an X next to the 150 milliliters. Now to work out X, we are just going to simply put an X over 0.9, which is equivalent to 150 over 100. So to work out X, we just need to cross multiply, which is 0.9 multiplied by 150 divided by 100, which gives us an answer of 1.35 grams of sodium chloride. Now 1 molar solution of sodium chloride contains 1 mole of sodium and 1 mole of chlorine. And the molecular mass of sodium chloride is going to be 23 plus 35.5, which is 58.5 grams. So 1 mole equals 58.5 grams. We don't actually know how many moles are present in 1.35 grams of sodium chloride. So we're going to do another equation. X over 1 is equal to 1.35 over 58.5. So to work out X, we're just going to cross multiply, which is 1 multiplied by 1.35 over 58.5, which gives us an answer of 0.023 moles. Our final answer needs to be in millimoles, so we just need to multiply that out by a factor of 1000, which gives us 23 millimoles. Study Day Calculations Paper 2, Question 8. You are working in a hospital pharmacy and need to prepare 150 milliliters solution of magnesium chloride, the molecular weight being 203.3, containing 4 millimoles per 10 milliliters of magnesium. What weight of magnesium chloride is needed to make this solution? Give your answer to 3 decimal places. So the relevant part of this particular question is the 150 milliliters that we need to prepare, the molecular weight of magnesium chloride, the 4 millimoles per 10 milliliters of magnesium, the weight of magnesium chloride, and 3 decimal places. So how many millimoles are present in 150 milliliters? Well, from the scenario, we already know that 4 millimoles are present in 10 milliliters. So X millimoles are present in 150 milliliters. So if we take X out, we've got X over 4, which is equal to 150 over 10. And if we multiply this out, we'll have 4 multiplied by 150 over 10, which gives us an answer of 60 millimoles. And 1 mole of magnesium chloride contains 203.3 grams. And remember, 1 mole is equivalent to 1,000 millimoles. So in 1,000 millimoles, we have 203.3 grams. So how many grams are present in 60 millimoles? To work this out, I'm going to multiply 203.3 by 60, divided this by 1,000 to give me an answer of 12.198 grams. And that is our final answer. Study Day Calculations Paper 4, Question 3. You are working in the specials department and are required to prepare 3 litres of a solution of sodium gluconate containing 25 millimoles per litre of calcium ions. The molecular weight of calcium gluconate is 448.4. What is the weight of calcium gluconate required to produce the solution? Give your answer to 2 decimal places. So the parts of the question that we are going to highlight are 3 litres of solution containing 25 millimoles per litre of calcium ions, the molecular weight, which is 448.4, and the question is asking us what the weight of the calcium gluconate is required to prepare the solution. And this answer needs to be given to 2 decimal places. So we're making 3 litres of the solution at 25 millimoles per litre. So how many millimoles are present in 3 litres? We can simply work this out by multiplying 25 millimoles by 3. And this gives us an answer of 75 millimoles in total present in 3 litres. The molecular weight of calcium gluconate is 448.4, and we know that this is equivalent to 1 mole or 1,000 millimoles. So therefore, 1,000 millimoles contains 448.4 grams, and we need to work out how much 75 millimoles weighs. And to do that, all we need to do is divide 448.4 by 1,000 and multiply by 75 to give us an answer of 33.63 grams. Calculations Paper A, Question 7. A 64-year-old patient has a foot ulcer. She has been prescribed potassium permanganate solution to regularly clean this wound. How much potassium permanganate would be required to extemporaneously prepare 200 milliliters of a solution so that when 5 milliliters of this solution is diluted to 1 litre, it gives a strength of 1 in 5,000. Give your answer in grams. So for this particular question, I'm going to start off by highlighting 200 milliliters because that's the final volume of our solution. Also, I'm going to highlight 5 milliliters, 1 litre, and then also 1 in 5,000. We need to answer our question in grams, so that's also important. So because we're making 1 litre of a 1 in 5,000 solution, what does this exactly mean? Well, a 1 in 5,000 solution is essentially the same as 1 gram in 5,000 milliliters, and we are preparing 1 litre of this, which is the same as 1,000 milliliters. So how many grams are present in 1,000 milliliters? A simple calculation will tell you that that is 0.2 grams in 1000 millilitres. You therefore have 0.2 grams of potassium permanganate in 5 millilitres of the solution. So when you're scaling up the 0.2 grams per 5 millilitres to extemporaneously prepare 200 millilitres, you are going to require how many grams? Again, a simple calculation will tell you if 0.2 grams are present in 5 millilitres, then you're going to have 8 grams present in 200 millilitres. So the final answer is 8 grams. Calculations, Paper C, Question 17. A 13-month-old child weighing 9.5 kilograms is being treated with chlorpromazine hydrochloride at a dose of 500 micrograms per kilogram every 6 hours for 7 days. The consultant has asked that each dose is contained in 5 millilitres. You have available chlorpromazine hydrochloride oral solution 5 milligrams per 1 ml. How much diluent will you require when making up enough chlorpromazine solution for 7 days of treatment? Give your answer in millilitres. So first of all, what I'm going to do is I'm going to highlight the weight of the child, which is 9.5 kilograms. We're also going to highlight the dose of 500 micrograms per kilogram every 6 hours for 7 days. And we're also going to highlight the 5 millilitres and the available chlorpromazine solution as 5 milligrams per ml. Now we want to work out how much diluent we require, so I'm just going to quickly highlight that. And that's going to be for 7 days of treatment, and our answer needs to be given in millilitres. So the first thing that we need to do is we need to work out what the dose actually is. So we can do this by multiplying 500 micrograms by 9.5 kilograms to give us 4,750 micrograms. Let's convert this into milligrams. All I need to do is divide by 1,000. So that gives me an answer of 4.75 milligrams, and that needs to be contained in a 5 ml dose as stated by the question. Now, chlorpromazine oral solution is available as 5 milligrams per millilitres, so we need to work out how much of this solution contains 4.75 milligrams of our required dose. So 4.75 multiplied by 1 divided by 5 gives us an answer of 0.95 millilitres. So in each 5 ml dose, 0.5 millilitres is going to be chlorpromazine oral solution. But the question is asking us how much diluent we require. So all we need to do is take away how much chlorpromazine we have in our solution, and the leftover quantity will be our diluent. So that's going to be 5 millilitres minus 0.95 to give us an answer of 4.05 millilitres. And that's going to be our diluent. Now, the question has asked us to work out a 7-day course, but the dose is 4 doses a day because it's every 6 hours for 7 days. So in total, we're going to do 4.05 multiplied by 4 multiplied by 7 to give us an answer of 113.4 millilitres, and that's our final answer. Calculations, Paper D, Question 13. You are required to produce 500 millilitres of potassium permanganate solution such that when 2.5 millilitres of it is diluted to 75 millilitres with water, it gives a 0.125% weight per volume solution. What weight of potassium permanganate do you require? Give your answer in grams to 1 decimal place. So for this particular question, we are going to highlight 500 millilitres, 2.5 millilitres, 75 millilitres, and 0.125% weight per volume solution. What we are highlighting will follow a similar trend, so if you haven't watched Understanding Dilutions tutorials, it might be a good place to start there. From our question, I'm going to highlight weight of potassium permanganate and the answer in grams to 1 decimal place. So if I dilute 2.5 millilitres to 70 ml, that in effect has been diluted 30 times. So if the final solution is 0.125%, then the starting solution is going to be 30 times stronger. So 0.125 multiplied by 30 equals 3.75% weight per volume. Now, a 3.75% weight per volume solution contains 3.75 grams in 100 ml. But the question has asked us to work out how much is contained within 500 millilitres. So we can simply work this out by multiplying 3.75 by 5 to give us an answer of 18.75 grams. Now the question has also stated we need to answer in 1 decimal place. So that's going to be rounded up to 18.8 grams. Study Day Calculations Paper 1, Question 8. You are required to produce 200 millilitres of a solution of potassium permanganate such that when 50 millilitres is diluted to 200 millilitres, a 1 in 400 solution is produced. You have available a stock solution of 10% weight per volume potassium permanganate. What volume of 10% weight per volume potassium permanganate solution will you require? So for this particular question, we are going to highlight 200 millilitres, 50 millilitres, 1 in 400, and also the stock solution of 10% weight per volume. From the question, we're going to highlight the volume of 10% weight per volume. So let's start off by working out if 50 millilitres is diluted to 200 millilitres, then how much are we diluting it by? Well, 50 to 200 has been diluted by a factor of 4. So if we're diluting by a factor of 4, we're going to produce a 1 in 400 solution, as stated by the question. The original solution must be 4 times stronger, so that's going to be 4 grams in 400 millilitres. But we are required to make a 200 millilitre solution. So if we have 4 grams present in 400 millilitres, we're going to have 2 grams present in 200 millilitres. Now our stock solution that we're going to create the solution out of is a 10% weight per volume solution. 10% is equivalent to 10 grams in 100 millilitres, and we need 2 grams, so how many millilitres is that present in? We can work this out by dividing 100 by 10 and then multiplying out by 2 to give us an answer of 20 millilitres. Calculations Paper A, Question 1. A 46-year-old patient has been given drug X, which has a half-life of 8 hours and is administered by IV infusion. Immediately after administration, the patient's plasma level is 80 micrograms per milliliter. What would be the plasma concentration after 40 hours? Give your answer in micrograms per milliliter to 1 decimal place. For this particular question, we are going to highlight the half-life of 8 hours. We are also going to highlight the patient's initial plasma level of 80 micrograms per milliliter. From the question, we're going to highlight 40 hours. Our answer needs to be in micrograms per milliliter, and it needs to be to 1 decimal place. With half-lives, it works quite simply. Each reading of plasma level will be half of the previous one. So because our half-life is 8 hours, we're going to be working in multiples of 8 up until we reach number 40. So we're going to have 8 hours, 16 hours, 24 hours, 32 hours, and 40 hours. And like I said, we simply just need to half 80 consistently. So at time 0, we're going to have 80 micrograms per milliliter, and after 8 hours, it's going to be half of what we had at 0. So that's going to be 80 divided by 2, which is 40. After 16 hours, that's going to be half of what was present at 8 hours, so 40 divided by 2, which is 20. At 24 hours, that again is going to be half of what was present at 16 hours, so 20 divided by 2, which is 10. At 32 hours, it's going to be half of what was present at 24 hours, so that's going to be 10 divided by 2 to give us 5. And finally, we've reached 40 hours, so that's going to be half of what was present at 32 hours, so that's going to be 5 divided by 2 to give us 2.5 micrograms per millilitres, and that's our final answer. Study Day Calculations Paper 2, Question 6. A 23-year-old patient has been admitted to hospital following a drug overdose. The half-life of the drug is 16 hours. The plasma concentration was 64 micrograms per milliliter when it was measured. What would you expect an approximate plasma concentration to be after 48 hours? So let's start off by highlighting the half-life, which is 16 hours, and the plasma concentration of 64 micrograms per milliliters. From the question, we're going to highlight the approximate plasma concentration after 48 hours. So following the same principles that we applied to our previous question, we know that we are going to need to work in multiples of 16 to get to 48 hours, and we're going to have to half our plasma concentration each time. So at time 0, we start off with 64 micrograms per milliliters. The next plasma concentration that we're going to measure is going to be after 16 hours, then it's going to be 32 hours, and then it's going to be 48 hours. Because remember, we're working in multiples of 16. So at time 0, we had 64 micrograms per milliliter. So after 16 hours, we're just going to divide the number from 0 hours by 2. So 64 divided by 2 to give us 32 micrograms per milliliters. The same principle after 32 hours, so 32 divided by 2 to give us 16 micrograms per milliliters. And then after 48 hours, we're simply going to divide 16 by 2 to get 8 micrograms per milliliters. Study Day Calculations Paper 2, Question 5. A 62-year-old patient has been admitted to hospital with septicemia. He has been given an IV infusion of piperacillin at an infusion rate of 0.5 grams per hour, which gives a steady-state plasma concentration of 0.08 grams per litre. We have been provided with some values of the volume of distribution, half-life, and the elimination rate constant. We have also been provided with the formula. What should the infusion rate be changed to such that it gives a new steady-state plasma concentration of 0.15 grams per litres? We're going to highlight the infusion rate of 0.5 grams per hour from the question. The values that we've been provided at the bottom, so our volume of distribution, half-life, and elimination rate constant, are all going to be used in this question. However, the steady-state plasma concentration that's been specified in our scenario of 0.08 grams per litres is not going to be used or highlighted in this question, simply because the question has asked us to calculate what the infusion rate needs to be changed to with a new steady state plasma concentration of 0.15 grams per litre. So that's the value that we're going to be using in this scenario. Now, if you look closely, you'll have two formulas that you need to work with. You've got the overall steady state plasma concentration formula, and you also have the elimination rate constant formula that we're going to use. So our value is 0.15 equals the infusion rate, which we don't know yet, that's what we're working out, divided by the volume of distribution, which is 11, multiplied by the elimination rate constant, which is 0.693, divided by 1.25, which is our half-life. Now, because we need to work out what the infusion rate is, we need to rearrange the equation so that we can work out what the infusion rate should be changed to. So I'm going to multiply the bottom half of the equation out so that I have 0.15 multiplied by 11 multiplied by 0.693 divided by 1.25. And that gives me an answer of 0.91476 grams per hour. And if we turn this into milligrams per hour, we can simply multiply this out by a factor of 1,000 to give us 914.76 milligrams per hour. And then we're going to round up to the nearest whole number, which is 915 milligrams per hour. Study Day Calculations Paper 5, Question 6. A 73-year-old female patient has been taking digoxin tablets, 250 micrograms daily, as maintenance for atrial fibrillation. She has been admitted to hospital having had a stroke and now cannot swallow her tablets. The ward inform you that they have digoxin solution for injection available, 250 micrograms per milliliters, but they need to know what volume of this to give. The bioavailability of the digoxin injection is 1 and the bioavailability of the digoxin tablets is 0.7. What is the equivalent volume of digoxin injection to be given? Give your answer to one decimal place. For this particular question, we are going to highlight the current dose, which is 250 micrograms daily. We are also going to highlight the injection solution that's available, which is 250 micrograms per milliliters. And we're also going to highlight the bioavailabilities of the different formulations of digoxin. Now, we need to know what the equivalent volume of digoxin needs to be given, and we need to answer this question to one decimal place. Now, the formula that we're going to use to answer this question is the amount in systemic circulation equals the bioavailability multiplied by the salt fraction multiplied by the dose. Now, the tablets provide a bioavailability of 0.7 multiplied by a salt fraction multiplied by 250 micrograms, which is the dose of the tablet that we have been provided. And if we swap it over to the injection, that gives us a bioavailability of 1 multiplied by the salt fraction and multiplied by the dose injection. We're going to rearrange this equation so that we can remove the salt fraction from both sides, so that overall the dose is going to equal 0.7 multiplied by 250 micrograms divided by 1. This gives us an answer of 175 micrograms. Now, the ampule contains 250 micrograms per milliliters, so we know that we need to provide the patient with 175 micrograms to give them an equivalent dose of the 250 microgram tablet that they're currently taking. So all we need to do is divide 175 micrograms by 250. That gives us an answer of 0.7 milliliters. Your feedback is extremely important to us, so please scan the QR code, give us a rating, and tell us what more you'd like to see.